So, just a short self-introduction before starting to kill zombies on stage. My name is Stefano. I'm an associate professor at Politecnico in Milan. And I'm here with my colleague, Roberto, who is a security engineer at Secure Network, a penetration testing firm, to talk about IoT vulnerabilities, and in particular, to talk about all of the zombies that are coming out of their graves to bite us from IoT. This talk is actually a modified version of a longer talk that was meant for developers who have no knowledge about security, so as an introduction. And instead, for you guys, we basically cut out the introduction and we added some considerations on what we think are the strategies for handling secure development in IoT. So I let Roberto start with the cutting of the introduction part.
Yeah, okay, thanks. IoT is almost everywhere, and we have seen a lot of stuff that is literally stuff. We have seen smart hairbrush, smart wine bottles, egg trays, and salt shaker. And the smart salt shaker didn't even grind salt. So we're talking about stuff, literally. Problem is that stuff is going to be inside your home network, and it's going to be connected, and it's going to be able to access any other device in your house, which might be useful, might be something that you need, or something that is helping you, like a thermostat, or a key ring that always knows where you are, or where any of your relatives are, and your irrigation controllers. And that's pretty scary until you consider that there are other IO things that are not that good to have compromised or inside the same network with a salt shaker. For example, cooperative robots that are supposed to work next to humans and have the power to do stuff that humans are not able to. So not something you want to be remotely controlled. Or insulin pumps. Your insulin pumps might want to update to patch vulnerabilities, so it's going to need internet access somehow, and it's going to try and expose some services, maybe, I don't know, to something that you bought to make your hair look beautiful. So that was pretty scary. And also, if you consider automotive and surgical robots, those are not something that should be either exposed or containing any vulnerabilities. At least they shouldn't. We know it's not possible, but at least that should be limited. So I'm not going to bother you with the threat modeling. That's already bad. The introduction is bad enough. So we tried to dig down into IoT code, and one of the first things that I found was this one. The fun part is actually the comment, because it said, print the required string in a protected way, and it is an SM printf that doesn't check for the format string. So this is just remote code execution 101, because we had control on the SRC parameter, which is just a format. And that was a pretty easy RCE on a thermostat. Not that scary until we found a plain buffer overflow in POS. This code was running on a POS, and it just kept reading characters until it was okay with it. Problem is, it didn't check for length. And the most annoying part in this is not just, this is a very old vulnerabilities. We're talking about something that is older than me.
It's Roberto's birthday today, so it's like 26, and these are 30 years old, whatever it is, so we can definitely state that.
But the most annoying part is that this is an fget. This is an fget-s re-implemented for no reason at all, and that would have probably worked even more efficiently. And this is something we found on POSes, but it gets worse.
Yeah, because a POS is actually a pretty critical device in many cases, but it's, when things get bigger and worse, and this is a half-ton robot by ABB that is very helpfully like 1 floor above my lab at the university. So it was kind of a prime target, of course. And when we started looking into it, so I'm no robotics expert. I took robotics classes at the university. I can pretend with you to be a robotics expert, but not with a real robotics expert. So when we started working with this, the first thing that you do, you dive in the manuals, right? The first thing that you do, you hit the books. So we hit the book. And this is a passage from the operating manual of Robot Studio, which is the software of ABB robots. And it says, all controllers have a default user named default user. We have a default password robotics. And this is already bad. But then the next sentence, the default user cannot be removed, the password cannot be changed. However, you can remove blah, 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 which means that you don't want to do that. No robotics person ever has touched these settings, because if the manual says you cannot remove it, you better not remove it. Now, from Robotware 6.04, which is like last year, guess when, it is possible to deactivate the default user. But this means that basically all of these robots, until the ones deployed last year, probably have these active by default. And even in those deployed last year, you need to specifically go in and deactivate the default password. And then people would just say, oh, okay, so the default password is not that relevant, right? This is a robot. It's not connected to the internet at all. So if this is not connected to the internet, then you need to explain to me why this thing runs a web server. But that's a side story. So one of the interesting things is that the robot is not really controlled by a single computer, right? There's multiple devices inside. So, and the only computer of the robot that is connected to the outside is the main computer. But there are other devices, and there's code on these devices that needs to be updated. So there needs to be a way for the robot to update the code. So we looked into how the robot updates the code. So these devices are connected via Ethernet, and they update the code using FTP at boot. So when the robot boots...
Make no mistake, FTP, not SFTP or anything like that.
No, just FTP. FTP. It's plain old FTP. And basically, when the robot boots, the devices that are not the main computer connect to the main computer and download their stuff from the main computer. With which user and password? We went back with memory and said, oh, okay, this is it. This is why you have the default user and default password, right? They need to log in with that. That's why you cannot remove it. No, wrong. Because you can use any user and any password. Because for the first 5 minutes after boot, user authentication system is disabled specifically to allow the various components of the robot to download their stuff. So, at that point, one may wonder if there is any code signing going on, code verification. Of course not. There's no code verification. There's not even a verification that whatever is downloaded is actually a system image. Whatever you download from there, it just boots. If it's a block of zeros, it will slam it in memory and try to boot it. So with predictable results. So then we wondered, okay, so this is already kind of strange. How do these things configure themselves? And then you see that they retrieve something from a path called /command with the startup information. And basically, you find that retrieve from /command retrieves information obtained by executing a command. And of course, if you, instead of retrieving, you put something into the /command of that FTP server that has been dutifully re-implemented. It's not a standard FTP server. It's a thing that the guys at ABB wrote for their robot. You can execute commands, of course, within the first 5 minutes without any credentials. And guess what? Do you really think that this FTP server is bound only on the inside in that computer, in that architecture that is connected to the inside and to the outside? Of course not. This is connected also to the outside. So from the outside of the robot, you can either use the already provided default password, Or you can wait for the robot to reboot, and you can execute any commands that you want on the underlying operating system. Then we looked into how this thing was implemented. And by the way, this is a decompiled version of the code, because the guys didn't strip it. So you can decompile it, and it decompiles to beautiful C code that allows you to see that inside this C code, there's a beautiful, straight from the book, 1997 buffer overflow that you can exploit as it was exploited originally in Smashing the Stack for Fun and Profit, because this thing is running on an operating system that has no ASLR, no stack protection, nothing. It's literally like I was doing it in 1996. So this stuff, I was able to write an exploit for it, and God knows I'm not an exploit writer. So this stuff is a zombie vulnerability matryoshka. There's zombies inside zombies of vulnerabilities, all in the same piece of software. And I said piece of software, care about it. So so all of this stuff is carefully hidden in industrial infrastructures, behind firewalls. Thank you very much for laughing already. So this is an example of one of those firewalls. It's not the firewall of which we are showing the vulnerabilities, and I will let you know in a minute why. It's called an industrial router. Basically, it's a glorified supermarket-level firewall. And if you look at the code that this firewall is running, the interfaces of this firewall, the ones exposed to the outside, are written in PHP. And in particular, we found this piece of code on it, on one of these, not this one other. We found this piece of code, and this piece of code, basically, you cannot even say which vulnerability this piece of code has, because it has all of them. It just picks up the variables from get and slams them into whatever code is in the backend without checking anything. It has all of the vulnerabilities at once. And so we said, okay, so this is mind-boggling. How is this even possible? One of my colleagues had an illumination, and he Googled a piece of this code. Turns out that basically this thing was picked up from a 2009 post, create this type of APIs with PHP, which has been since deleted by the authors. You can only find it on the archive machine.
Probably out of shame.
Yeah, probably out of shame. And this has been copy-pasted in a thing that costs $8,000 to buy. And it's the only thing, literally the only thing that separates robots that cost $70,000 and run production plants from the internet. Oh, and by the way, the reason why this is not that is that the vendor of these has never gotten back to us about how to fix this. In fact, they actually showed up after a talk about this vulnerability was given at Black Hat. They gave us their cards after we had been trying to get in touch with them for like a year, and then they disappeared again. And we don't know up to this day why they gave us their card. We don't know exactly, but still. So, oh, and by the way, this table shows that there's thousands of these type of routers connected directly to the internet. 5,000 of those are without passwords. I leave that for your consideration. So since some of these vulnerabilities are way older than Roberto, we actually would like to figure out a way to understand where these zombies come from. How is it possible that we have vulnerabilities that should be dead for 30 years in these devices? Because that robot software is not old. The usual justification that we have is that the industrial systems run old software. Not even the new software has old vulnerabilities, so there's something broken in there. So we started trying to figure out that, and we basically did this through a couple of ways. We engaged with the community of security professionals on Twitter. That's where security professionals live. If you want to find security professionals like piranhas in a tank, you throw a question on Twitter and then you walk away very fast and you see the security community going it. And in fact, we had basically 1,000-something interactions with the tweets for this discussion. And the discussion was very simple. We asked the community, what if you could give an advice or give a rule to embedded developers? They are developers. They don't know anything about security. What would the advice be? What would be the useful piece of advice to try to create a baseline for security protection of their code? So most of the tweets were things like, oh, yes, you need to start with threat modeling. So you learn threat modeling. And then after you have threat modeled your device, then you go and you read these 3 or 4 books. And then you try to... And we were like, no, guys, no, stop, abort. This is not the right answer. The other thing we did was we went to talk to embedded system developers. And what we found was very interesting. So one of this discussion, I was talking with one of my friends, and he has been working for TI for years, and he's one of the senior developers there. He writes the code that ends up in other people's code for IoT. And during the discussion, we were talking about vulnerabilities. At some point, I was talking about one of the vulnerabilities that we did not show here, about the string copy. And it was like, wait, what? Why is string copy a bad idea? What's the problem with string copy? And we're like, okay, we may need to do a couple of steps backwards here and start again. The other perception that most of the developers of embedded software have is that vulnerabilities is something that happens to the IT guys. They are not IT guys. They design things, and they do not have the problem of vulnerabilities. Vulnerabilities happen to the web people. And this is literally the answer that I got from some of them. So it is an embedded perception, embedded system community perception. There's a lot of old code there. There's a lot of technical depth. There's an enormous pressure in time to market. Many of these products come out and they are developed very quickly. So this is one of the reasons why we looked into SDKs. But in general, the perception from looking at what the security community was saying and looking at what the embedded systems development community was saying is that we are not talking to each other. We are shouting past each other. When a security person meets an embedded system person, they begin shouting at them because they are not doing the right thing. And the embedded system person is la, 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 la. I don't need to do that because I don't suffer from vulnerabilities. That's you guys. I don't care about you. And we are not providing very viable solutions.
So we started to try and reproduce at least an acceptable level of security on several SDKs and compilers for embedded tools. So stack smash protection is just not there. There is no ASLR, no not executable bit. CHECKSEC is not used, and for a long time, also GCC, which almost any one of us have used, for ARM, when compiling for ARM, did not enable stack protection. It was there, but by default, until 6 months ago, GCC would not just put canaries there. And that was bad enough. But then we tried some SDKs, and this was the outcome. This is the output of CHECKSEC. So nothing of the model anti-exploitation mitigation was there. Only an X, but that was just thanks to the architecture. It was just it. So we tried to work on that because, that was one of the most used SDKs ever used. I think it's TI SDK. So that should be somehow documented in some way. It is not, but it gets worse because we tried a different SDK, and after digging for like an hour to find anything security related, under the quality improvement optimization tab in the compiler, we found that we could...
So this thing is actually like 5 levels of options down. You need to go and dig in. It's not documented anywhere. It's also called the wrong way.
So when we were finally able to enable stack protection, which is really old as a mitigation, we were prompted with a question. And we had to read it 5 times, then we started to laugh, because it was asking us, what should the value of the canary be? And that's no surprise when
that's our random canary right there.
That's our random canary.
For two.
Yeah, you cannot guess that. until you read it, because it's statically compiled in the executable. But except for that, it makes no difference. That's not a canary, that's not stack protection, because anyone that has a copy of the executable is able to exploit it as if the canary wasn't there.
So before you have doubt, these are 2 or the 4 or 5 most widely used IDEs for development. It's not like the embedded guys do not use any number of tools. They have tool chains that are pretty much fixed. And this is a large part. I don't know the percentages. I'm no gardener. But this is a large part of the development chains. And I'm very sure that if we look into the other few IDEs, you will find them precisely configured the same way or misconfigured the same way.
So we guessed that there was just lack of tools, lack of, for example, testing. Testing on an embedded device is not easy, and it requires simulation of architecture that are not usually supported by QEMU or emulators like that. So you need a custom emulator, drivers. It's not easy. Moreover, there are no safe libraries to use. One of the developers we spoke with thought that the standard library had to be secure because, I mean, it's standard, right? So how could I possibly put a vulnerability in my code if I use standard library functions? And when we tried, and I think we spent several days trying to find a secure library, or at least a safer one, to develop in embedded C, we just didn't find any, because they're not there. We can recommend something, but they're not what we were looking for, or something that should be there. Moreover, in SDKs,
there's no drop-in replacement. There's no libraries that you can just use to have wrapped for you security and safe things. Well, this is normal. We know that this is happening. This has been happening in ICT for ages. But at the very least, we do have some protections built in by the compiler, and most compilers complain loudly about unsafe uses. And this is not the case, as we will see. Also, inside the SDKs, we found code that was not vulnerable, because the people developing this stuff are actually pretty good. But they were not vulnerable because of a side effect.
Yeah, checks were performed before calling sprintf. So buffers were checked, but snprintf wasn't used. So anyone that copied just a part of that code would get a vulnerable version of it, because checks were usually performed like 5 calls deep in the stack before the buffer was actually filled. So we tried to enable everything. This is TI IDE. We enabled any security check that we could find, any quality improvement check. And then we wrote a getS into our code. And if you ever tried to put a getS in your code and compile it with GCC, it complains. If you try to link it with Apple libraries, Apple standard libraries, every time you call getS, your program will accidentally print in standard error, you should not use getS. So they patched getS to warn you. To insult you, yeah, basically. And this was the output. The output is there. It's just saying that it created the empty parts of the executable, but no warning. Our getS was there, and this is everything we had. No warnings at all. So we tried to enable Misra C, which said you should not use any standard lib function. So we used the string.h library with a string copy, where we copied a buffer that was 10 times bigger than the other one into the smaller one. And we got the, we should not use those buffers before we assign any value to them. So the problem was not a buffer overflow that can be statically checked and found. The problem there was that the buffer was not initialized. That was the output of the most used SDK out there.
And one of the funny things is that use Misra C was one of the best suggestions that we found from the security community in how to tell an embedded developer how not to have vulnerabilities in their code. So that was probably the best suggestion that we had, and it fails miserably.
Yeah. Plus, we tried to look into the examples that were embedded into SDKs, and this is one of the best examples that we found. It gets parameters from the arguments, it gets the options, and then it just string copies to a statically buffer, to a statically sized buffer, whatever you pass to the executable. So it just writes whatever you give it in a portion of memory that was in the BSS, with no checks whatsoever. And that was a sample main. You see an int argc char argv. That is just not sanitized in any way. And we kept looking, because what else could we find in that thing? JSON formatting. You know, it's important if your IoT thing communicates in a proper way with the external devices or the hubs, and it's usually done via JSON format. But formatting here was just done with a simple format string, so there was no escaping. We could quote and unquote anything we wanted. We had got complete control of that JSON that was passed to another part of the code, which performed no checks too.
So when we started asking to the people from our field, okay, so suggestions. What do we give to developers? What weapons, what tools we give to developers? We found a lot of really unapplicable tools. It really looked like the zombie apocalypse, where people start trying to fight the zombies with a knife, which is kind of the worst possible tool that you can use.
Yeah, but with a quick scope.
Yes, with a quick scope. There's a number of these things that do not really work. So the first suggestion that we got, and we got it a lot, was, oh, they need to use fuzzing. Yeah, right. So we don't use it in security, but we kind of suck at it too. And you want the developer that has no security concept at all to put up AFL or libfuzzer and fuzz their code, for which they don't even feel the need to.
Plus, they don't even write tests.
Right,
so
they don't write tests. So, so the other thing is, somebody said, oh, okay, so in general, for C code, you can use an address sanitizer, ASIN. That's a very good suggestion. It cleans up a lot of stuff. Yeah, pity that the only non-supported combination for ASIN is Linux on ARM.
Which is never used in IoT, right?
Which is kind of the IoT main staple. I already ranted about the threat modeling, and don't get me wrong. I think that threat modeling for security people is like the basic starting point for a security assessment, for a penetration test. It's super important for us, but we cannot ask every single IoT developer in the world to do threat modeling in order to write their code. They're never going to do that. That's never going to work. Also, there was this other suggestion, which I found very curious. So we as security people always say consider input like untrusted. If you need to teach just one thing to a developer from a security standpoint, is check your inputs. That's probably the best single advice that you can give, which is true. But in the physical world, they have a lot of inputs that come in from sensors. And so when you tell a developer, look, this input that you got from sensors, you need to check it. They look at it and say, why? This comes from a thermometer. This comes from a compass sensor. This comes from a movement sensor. What can possibly go wrong in reading it and assuming that it works? Well, we as security people know what can possibly go wrong, but they don't. And they will never think of that. Oh, and the others, my personal favorite was the guy that said, okay, you can patch this specific call inside the kernel in order to have the device reboot, as opposed to returning 0 from a malloc because it cannot allocate memory. And I'm like, yeah, this is actually a good idea. Rebooting the device instead of failing a malloc could be a good idea. But are we really thinking that everybody that develops something for an embedded system needs to rewrite piece of the kernel in order to secure their code? Are we completely out of our mind?
And actually, you don't want developers that are usually not able to protect against buffer overflows to change the kernel code. That is something that should just never happen. But I think one of the funniest comments we read was like, well, of course, there are problems, but they're also in the compilers. So whenever you compile your code, you should be careful and read the assembly output of your compiler to check if the compiler maybe didn't mess up your crypto code. And it was so wrong, just because why do you have your own crypto code in the first place? But except for that, I don't know how good are you at reading assembly that is produced by a compiler. I'm not very fluent in that, and I don't expect any developer to have the time to go and read like 5,000 lines of assembly code.
If you have the time to reread and double-check the assembly produced by your compiler, probably you can write assembly in the first place and just be done with it.
Yeah. So, since we didn't want to be too negative and pessimistic about it, we tried to find a solution. Fun part is that the second entry in this slide, we didn't change that just as a proof of concept. We thought that Misra C would solve something. It solves something, but it just doesn't protect you enough. And what we found is that we as a community, we should start creating safe libraries. We should have solutions. I mean, we have a lot of conferences and a lot of projects for attack, for offense. And we have little to defend ourselves. And when we need to communicate with developers, we need to have an answer that is ready and already tested. We need to have something like cheat sheets that we can provide. We found some of them, but there are just 3 of them, and they don't really match. They don't really get the point. We should start creating guidelines. A developer doesn't want a 3 books long course on threat modeling. They want their checklists. And we need to provide them. It's our responsibility. Moreover, we should teach them to not reinvent the wheel. I mean, when you need to provide an update functionality to your software, use a library that is already tested. Don't write code from scratch.
So there are some tools. We know them. We know more than these. But these are the ones that we found that could be used by embedded developers. They were reasonably useful. However, they are definitely not enough. Also, they are not in their tool chain. They are in our tool chain. But they're not in their tool chain. They need to end up in their IDEs. Otherwise, they are not going to be used. Okay, so there's also this is an issue, and I want to conclude so that I leave time for question, but there is an issue that is typical in the IoT world because there's a lot of technical depth. So we tried to figure out ways for people that inherit a code base to actually go and dig for security vulnerabilities in it. And the grave digging is actually, it's already bad for us, and we know what we are looking for. It's even worse for the developers because they don't know exactly what they are looking for. They have the pressure to actually be able to change that code base. And most of these code bases do not have tests, are not linted code. It's code that is difficult to read. And we figured out a few basic advice, but I will not spend your time on those. There's a few links in there, so when we upload the slides, you can go and use those as links to throw at a developer that needs to learn something about security, even if some are way too long. So in conclusion, what we have found is that there's lack of awareness from the developer side, but this is, and we always blame that, and that's fine. But
and
then
that's
there's
not
also
something that we can really fix. We can help fixing that, but we can't fix it completely.
Except by shooting, but we need to shoot zombies and not developers. But there's a definite lack of tools and lack of solutions that we as a community provide. We don't provide them solutions. We tell them that they have a problem. And when they ask, what can I do in order to fix not everything, But parts of my program, at least the basic ones, we still don't give them checklists or anything. So thank you very much for listening to this rant, and we are open for questions.
Hi, I'm a developer, so please don't shoot me. And I do build some embedded systems, although with the Raspberry Pis and stuff like that. So I'm curious, I totally agree with your sentiment that there is a huge lack of awareness, and I've been talking to a lot of people in this conference about that amongst the development community. For the most part, developers know absolutely nothing about security and have no concept of it, and also have this hubris that it won't happen to them. So I guess what I'm wondering is, maybe not strictly for embedded, but maybe from that context, if you were to put it together a checklist, you said that the first thing on that checklist would be check your inputs. That's a pretty good and obvious one. But what are some more? What are your top 5 pieces of nuggets of advice that you would give the development community?
That's a good question for the audience. What are the top 5? Mine would be check for input. It could be another one is go and check your allocations of memory, because as we have seen, the operating system is not going to support you, and in limited memory systems, those allocations may fail.
Yeah.
And by failing, create issues.
I would also suggest to enable protections that are there. For example, if you use GCC, enable stack protector, not executable bit, anything that GCC allows you at least to mitigate. Some vulnerabilities are not exploitable thanks to modern security tools, so we just enable them in GCC. Moreover, don't reinvent the wheel. We have seen a lot of vulnerabilities in code that was already available in an open source flavor without those vulnerabilities, code that is being tested, sometimes reviewed, and we have seen people re-implementing that, which is costly, and not just that, it's dangerous.
Why do you think, and this is something that I tell people too, is don't reinvent the wheel. There's always something out there that's been tested way better than you, somebody who's smarter than you coded it. Like, if there's something out there, you should use it as, once you vet it and make sure everything's good. But why do you think that there is such a lack, and I don't understand this, why do you think there's such a lack of awareness that these things are out there and that it's a much better idea to use them, and then people go and just write their own crypto code or update logic or anything like that that's obviously a terrible idea, at least to us?
So specifically for IoT devices and embedded systems developers, I think I think that this is a very good question. I think one of the answers is most of these people are very used to limited power devices, very small. Most of them come from like microcontroller programming, and they are used to having to do everything. They don't even really think that there is something that has been taken care for them. And so they reinvent things. I mean, on the robot, they rewrote an FTP. Now, an FTP server is maybe not the most complex thing that you can write, but we all know that there's been God knows how many vulnerabilities in Vue FTPD over the years. And why should we be doing that all again on a robot? There's a lot of FTP servers that you can apply, and actually, maybe you can find a better way to distribute updates within your architecture that has already been written. There was a library called Mender, for instance, that does that. Why even getting to do that? It's Mender, right? In my opinion, it's like self-reliance. They are used to a very small device that they need to do everything on. And I don't really think in the terms that we are used to as software engineers, picking up libraries and putting them together, which has all its sorts of issues, as was demonstrated by Kimberly before talking about open source software development. So there's all sorts of issues there as well. But for sure, there's a number of things that have already been done. Oh, another of my personal favorites, which we actually didn't mention so far, is that in one of the tests, we found a very curious modification of the kernel. Oh. A modification in the stack of TCP/IP.
Yeah, in order to close a port, instead of ending a thread that was listening on the port, they patched the kernel and implemented a new syscall that, when triggered, would change the TCP/IP loop, main loop in the kernel, and would just skip reading the packet if the port was supposed to be closed, which is...
Guys, I wish we were joking.
Yeah, I wish to. Point is that they skipped too much, so they didn't deallocate the packet afterward. But except for that, it was kind of safe, I think. It's not something you would expect.
Just weird.
Just very weird.
So it's a lack of awareness of the state of the industry and what's available.
And a lack of awareness, I think, in the seeing systems that are compositions of smaller blocks instead of being monolithic things. Because at the end, if you're looking at embedded development, many of embedded systems do not really have this separation with the operating system, the application. You're developing everything and just slamming it into an executable and putting it on the device. So there was a question back there.
Also,
I just wanted to make a comment because you were saying what are the top 5 things that as a developer you do. I think one for me, and it's more relevant now than it has been, is, and especially at our company as well, is not checking in passwords. So username and passwords, keeping those out of the code, which seems pretty simple, but a lot of those...
Do not hard code any credentials.
Yeah, hard coding credentials, S3 buckets, anything that you consider sensitive that could essentially be taken and automated and then exploited in some form is just simple.
I totally agree. Yeah, I totally agree, but I will throw one thing out so that you can think about it, because it's not an easy problem. It sounds like an easy problem, it's not. If you are an embedded system developer and you need to inject a credential into each embedded system that you are putting out of a factory line, like a key that needs then to be used to connect to the device. And you need to do this because we all know how to do this. Doing this on one device is easy, but you need to do this on a production line. And you need to be able to do this in a way that allows other people to pick that up and automagically connect to it. This is a problem that we don't really give as a software community or security community a good solution for. And it ends up with people in a better left unnamed brand of cars, which have handles that pop out of the doors. Each of those handles is controlled by a single ECU. And don't ask me how we know it, but at some point during the development of this specific vehicle that nobody has understood which one is it, they had issues with these handles popping out in different order badly. And they realized that all the ECUs were responding to the same identifier. So until they found a better way to engineer the process, before these vehicles rolled off the assembly line, there was somebody manually connecting to each of the 4 ECUs in each vehicle and changing the identifiers to different things, so that they would not mistakenly pop out from the wrong door when passing in front of one of the sensors. So this is a very stupid problem. But we as a security community, if an embedded developer asks you to solve this problem in an engineering sound way that can be put in a production line, I assure you, it's not an easy problem at all.
So this is a little bit of a leading question because I think I know the answer, but for these different IoT devices that you looked at, whether it was a hairbrush or a robot, had they thought about an update mechanism for when flaws were found and they had to push out new software?
Thanks for the question, Roberto.
The short answer is no. We found some some attempts to make it updatable, and some did in a poorly written and secured way, and something else just didn't. The only way to update most of the devices we tested is to manually connect to it on a debug port and flash a new firmware on it. So not something I would ask users to do.
Yeah.
Create an update system should be in the checklist. Yeah, we should start writing that.
We should start writing
and don't write to your own, yeah.
Okay. Thank you very much.
Well, thank you very much.
Thanks.